Welcome back to this second part of our introduction to DeepRL. In the first section, we started by discussing how deep neural networks can be used for function approximation in RL, and how automatic differentiation specifically can support doing so with relative ease. And then we delved into the issues that arise when doing so, when using deep learning for function approximation. So for instance, we discussed how the different choices that we make on the RL side affect the learning dynamics of approximate value functions through phenomena such like the deadly triad or leakage propagation. Several of the issues that we discussed though were ultimately issues of inappropriate generalization. So today I want to talk about some of the ideas that can be used to help with this problem by tackling directly the fundamental problem of representation learning in RL. And I want to stress that this is far from a solved problem. So what I will discuss today is, you can see it as a partial snapshot of recent research on this challenging issue, but not an ultimate answer. But the main insight that underlies many of the things that we will discuss today, I think, is quite important, and is that so far our agents optimize the representation for a very narrow objective, purely the prediction or maximization of a single scalar reward. And this narrow objective is the only thing that is driving the entire representation learning in our DeepRL agents. And this has some advantages. So the ability of building flexible, rich representations that are kind of tailored to the specific task at hand is after all the main reason we use deep learning in the first place. But it does come with some disadvantages, because such a narrow objective can induce an overly specific, overfitted state representation that might not support good generalization. And this in turn can make agents even more susceptible to issues like the deadly triad. And if you agree with this premise, then maybe the natural step is to ask our agents to learn about more than just a single task reward, have them strive to build richer knowledge about the world. But of course, this is, in a sense, is easier said than done, because in order to do so, we need to think of, what other knowledge should they learn about? And there are many possible choices. And since representation learning is not a problem that is exclusively to RL, we can also tap into supervised learning literature for some inspiration. But among the many possible ideas that can help build these representations, I want to focus on two families of ideas that have attracted a lot of interest among RL researchers in the past years. And these are general value functions and distributional value predictions. So let's start with the first, general value functions. If you recall from the beginning of this course, RL is based on the so-called reward hypothesis that states that any goal can be represented as the maximization of a suitable scalar reward. And this hypothesis was originally discussed to argue that maybe RL as a whole is a sufficiently formalism for intelligent goal-oriented behavior. But today I want to use this hypothesis to make a different point and argue that if this is the case, maybe then all useful knowledge that the agents should or could aim to collect in order to support learning can also take the form of predictions about suitable cumulative scalar signals. But importantly, this predictive knowledge does not need to refer to the single main task, so-called reward. Instead, the agent could make predictions about many different other scalar quantities. And these predictions would still look very much like value functions, but it would refer to a different scalar signal, and are therefore typically called general value functions. The general value function is, in a sense, very much like a standard value function, in that it is a prediction about the expected cumulative discounted sum of a suitable scalar signal under a given policy. But in general value functions, we make explicit this dependency on the scalar signal c, a discount factor gamma, and the policy pi, because we are open to make different choices for each of these. So in the GVF language, the scalar signal c that we choose to predict will be called the cumulant, while the discount gamma associated with GVF will still define a horizon for the predictions that we make about that cumulant, and the target policy pi is going to be an arbitrary behavior under which we compute expectations. This will not necessarily be the agent policy. Of course, this may still feel a bit abstract, so let's be even more concrete and let's consider some examples. So if the cumulant is the main task reward, and we compute the expected discounted cumulative sum of this signal under the agent policy and under the agent discount, then the GVF prediction problem just reduces to canonical policy evaluation. That is the problem that we have dedicated so much space in previous lectures. But if instead, for instance, the cumulant is still the main task reward, and we still predict it under the agent policy, but with a discount of 0, well, then this becomes an immediate reward prediction problem. And we are not forced to have only one prediction that we're making, so we could have n cumulants, each corresponding, for instance, to one of the state variables or one of the features. And if we predict these under the agent policy with a discount of 0, then this becomes a next state prediction problem. And of course, we can go on and on. We can consider many different cumulants, many different horizons, many different hypothetical behaviors on which to predict these cumulants. And the beautiful thing about the GVF frameworks is that it allows us to just represent this very rich knowledge about the world, but learning all of these predictions with the same mechanism. So for instance, we could use the same TD algorithms that we reserved to make value predictions for the main task reward to predict any of these. And the main problem then becomes not how to learn such knowledge, which in some sense we can address with the standard RL, but how do we use these predictions, this rich knowledge about the world, to provide our agents with good representations that can support fast learning, effective generalization, and all the things that we're after. One beautifully simple approach would be to use the GVF's predictions directly as representations. And this is what is called predictive state representation, or PSR. And it's based on the argument that for a sufficiently large and sufficiently diverse set of GVF predictions, these will be sufficient statistics for any other predictions that we might want to make, including, for instance, the value predictions for the main task reward. Therefore, we can use the GVF predictions themselves as state features and then learn values or policies for the main task as linear functions of these predictions. And this actually has a number of appealing properties, and so I would encourage you to read the paper linked at the top to learn more about this. But it's also not the only way of using GVF predictions. Another option for how to use GVFs for learning state representations is to use them as auxiliary tasks. So this use of GVFs resembles a number of techniques from supervised learning, where forms of auxiliary tasks have been introduced to help with representation learning. So think, for instance, to the self-supervised learning objectives that are common in computer vision. And this approach has the advantage of being especially well suited, I think, to deep RL agents, because the compositional nature of neural networks allows to combine auxiliary predictions with the main task predictions with relative ease. When we use GVFs as auxiliary tasks, the way we typically do so is by sharing the bottom part of a neural network that we're using as function approximator between the main task prediction, so for instance, a policy prediction or a value prediction, and all of the auxiliary GVF predictions. And by doing so, what happens is that both the main task and auxiliary predictions become a function of a single shared hidden representation. And then both the shared and unshared parameters can be optimized by minimizing jointly the losses associated with both types of predictions. And the result is that the hidden shared representation is forced to become more robust and more general and encode more about the world. So this specific way of using GVFs as auxiliary tasks was, for instance, implemented in the Unreal agent. It was introduced by Jaderberg and a few others a few years ago. So in Unreal, a neural network is used to map input observations to both a value prediction and a policy prediction, because it's based on a fairly standard actor predict system. But additionally, 400 distinct cumulants are constructed as the average change in intensity of pixels between consecutive observations. And then an additional head is connected to the hidden representation from which we make value and policy predictions just after the end of the convolutional stack. And this auxiliary head is then trained to predict GVFs for each of these 400 cumulants. And these auxiliary losses are then referred to as pixel control losses and are just summed to the standard policy and value losses, and everything is optimized end to end. The same kind of system can also be applied if the observations are not images, or if the observations themselves were too big to use them directly to construct this large number of cumulants. So for instance, in the same paper, they introduce another related GVF-based auxiliary task, which is what they called feature control. Again, it works by constructing a large number of cumulants, but these are computed as the differences between the activations in the network itself between consecutive steps, instead of being differences in the intensity of pixels. But similarly to pixel control, once we have this large set of cumulants, however we derive them, they just learn the GVFs associated to each of these cumulants by having an auxiliary prediction head, again, that shares the bottom convolutional stack with the main task policy and the main task values, but then is forced to also support this additional auxiliary tasks and therefore learn a richer, more effective representation, basically. It may seem as a small change, but actually making these GVF predictions, either in the pixel control type or the feature control type, did make a real difference. So for instance, in this plot taken from the Unreal paper, you can see how using these auxiliary predictions, so the blue line labeled Unreal in this plot, delivered a huge improvement in the overall performance of an actor-critic system on a suite of challenging navigation tasks. And this is despite these auxiliary predictions only affecting the rest of the system through the improvement in representation learning. So for instance, we're not using them to implement PCR, for instance, or for anything else, except propagating gradients and updates into this shared representation. And it might seem surprising at first that how can it make all of this difference? After all, the cumulants that we are predicting these GVFs for don't seem to encode a particularly useful type of knowledge. They may actually seem somewhat arbitrary and contrived, and particularly in the pixel control setting. And even worse, we're not actually making use of the resulting predictions in any way. But if you consider, for instance, pixel control, making these predictions regarding the variation in intensity of pixels between consecutive observations actually requires the agent to understand many non-trivial aspects about the environment. For instance, how the agent actions affect the location of objects in the field of view of the agent. So even though they might seem a bit contrived, these representations actually force the representation to encode a lot of useful knowledge. And that is why they're likely to then make the representation more useful even for other tasks. And this, I want to stress, is particularly important and particularly useful in settings where maybe the main task reward itself is actually sparse and would therefore provide very little signal, at least early in training. While in contrast, these auxiliary cumulants that were constructed either from features or from observations can provide a very dense learning signal. And then it can help kind of bootstrap representation learning even before the agent has had the chance to see the first reward, for instance. And then when it does actually see these rewards, it can pick up on these more quickly and then learn much more effectively. To understand, though, why using GVFs as auxiliary predictions is actually useful, it's maybe worth thinking at what happens to the feature representation to try to understand what is the actual effect of this. So let's start with the linear function approximation case. So this is the plot on the left. And here we see that what happens in a reinforcement learning update to some value functions when we're doing linear function approximation is that we have some fixed feature representation, and we construct a target value function using a suitable operator, for instance, a one-step temporal difference operator. And then this target value is projected onto the space that you can actually represent under the fixed feature representation, and the parameters are updated accordingly. In deep reinforcement learning, this is the plot in the middle, we have a more complex phenomenon. Again, we construct some sort of target value function using a suitable operator, but then we project on the space of value that we can represent, not under the original feature representation, but a new one that is updated to have it support as well as possible this new value targets. So we have we're both changing the final value predictions, but also we're changing the representation itself to support these value predictions. So what happens when we add auxiliary GVF predictions, like the ones that we discussed with pixel control or feature control? Well, what happens is we're regularizing the second step. So we're preventing the representation from becoming overly specific to the current value predictions. And what we find, at least empirically, is that this regularization does seem to help quite a lot. But by itself, this interpretation, while it helps understand what happens when we use GVFs as auxiliary tasks, in a way, it maybe raises a bit more questions than it answers, because after all, isn't it desirable for the representation to be updated to support the value predictions as well as possible? So why should regularizing the representation help in the first place? And if it does, which GVFs would provide the best regularization? So let's try to answer these one at a time. So the first thing to keep in mind to understand why using GVFs to regularize representation is useful in the first place is that Over the course of learning, we will actually need to approximate many value functions. This is because if we're doing our job properly, in RL, the agents will get better over time. Therefore, both our data distribution and our value predictions, even in the same states that we have seen in the past, change as the agent's behavior changes. And this means that we want a representation that can support not just good value predictions right now, but it can support approximating all of the value functions in a way that on this path in value space that goes from the values of the initial policy all the way to the values of the optimal policy. Regularization can help us achieve this by preventing the representation from overfitting to the current value function, therefore making it more likely it will be effective for future value functions on the value improvement path. This is not that dissimilar if you think about it from what regularization is used in supervised learning for. This where with just the need to generalize from a value function to an X being akin to the need to generalize from a training set to a test set. The nice thing about, though, this value improvement interpretation is that it doesn't just give us some intuition about why regularization might help, but it also provides us a handle to think about the second question that we asked a few slides ago. So which GVFs should we predict to make regularization as useful, as effective as possible? If you remember, to construct a GVF to use as auxiliary task, you need to specify a cumulant and a target policy. So to try to answer this question of which GVFs might make the regularization more effective and as effective as possible, let's see how the choice of cumulants and target policies affects the type of representation induced by the use of auxiliary tasks as a regularization. So consider the space of all GVFs at first, considering two different policies, but all referring to the same main task reward. So this space of function, which geometrically speaking forms the polytope, will be depicted on this slide as a triangle. The value improvement path that we discussed before is then some sequence of value functions within this polytope that corresponds to the values of all the various policies that an agent passed through over the course of training. So this sequence will be depicted by the gray line that is within the triangle. Note that the value improvement path should always unfold in the direction of the optimal values, but the exact sequence depends on the initial policy. But in any case, for each given representation phi, that is here depicted by the straight black line, this will support different value functions more or less well. So to understand how the different choices of GVFs will affect this, will affect the learning and will make the representation more or less effective, we need to look at how the choices of the target policies and cumulants affects the representation and how this interacts with all of the other elements that we just defined. So starting from the left, first up we have the unregularized case. Here, representation learning is only driven by accurately predicting the current value function. So in this case, there is nothing to force the representation to be well aligned with any other value function except for the current one. So here we have a very strong risk of overfitting. In the second plot from the left, we instead consider the case where we include GVFs as auxiliary tasks, but these correspond to cumulants that are different from the main task reward. This means that their value actually lives outside of the polytope that we have defined, so outside of that triangle, and is visually depicted as these colored dots. Again, also in this case, there is actually no strong reason to believe that regularization will be especially well aligned to induce representation that support values along the value improvement path. But it does still at least seem to work empirically for certain choices of cumulants. So for instance, we saw that the pixel control cumulants in the Unreal agents helped a lot, and these actually correspond exactly to this second plot. But it's good to realize that there is no strong guarantee, and therefore it might be sometimes hard to pick suitable cumulants. The third plot from the left captures instead the case where we use GVF auxiliary tasks to predict the main task reward over a thin set of different target policies that differ from the agent policy. So now the representation is forced to support a range of values within the polytope, and given the geometric structure of this space of value function, it actually can be shown that for a suitable set and choice of policies, the induced representation will capture the principal components of the value polytope, and therefore provide good support to approximating values in the polytope and including the ones in the value improvement path. But unfortunately, the exact solution to construct the right set of policies is computationally intractable. So in the final plot, we show a concrete approach to picking these policies in a way that is instead tractable. And the intuition here is that the actual value improvement path, so the set of values that we will care to predict during the course of learning, is actually much smaller than the whole polytope of all the possible value functions for all possible policies. So maybe we should just target the values on this path. And at each point in time, while the future policies on the path are unknown, we do have already at least passed through some sequence of policies and associated values during training. This is basically the sequence of policies and values that we have been predicting so far. So rather than picking the policies arbitrarily, we could take advantage of the trajectory to pick a selection of policies as least aligned with the value improvement path up to the current moment. And by picking these past policies as the policies to use as targets in our auxiliary GVFs, then we don't guarantee that these policies will induce a representation that optimally supports future values, but at least it must support well the values on a subset of the value improvement path. And it provides us both an informed choice that is at least reasonable and a choice that is computationally tractable, because we have access to these because we went through these policies during training. And indeed, this choice of GVFs as auxiliary tasks was actually found to perform the best among all the choices that we discussed in a recent empirical study. Learning about multiple GVFs as auxiliary tasks is basically turning agent learning into a multitask problem, because we're now jointly training a shared representation to support many predictions that we can see as different tasks. And this is great for all the reasons that we discussed so far, but it can also introduce a few challenges. So when we want our agents to learn as much as possible about the world and make all of these additional predictions, we need to face the fact that we only have limited resources. So we have limited memory, we have limited representation capacity, computation, and so on. So different tasks will always find themselves competing with each other for these shared resources. So any concrete system will actually need to define some way of trading off these competing demands. And the important thing to realize is that there is always a trade-off. So even if you don't make it explicit, even if you don't do anything fancy about it, the system will make some trade-off. So for instance, the magnitude of the predictions and the induced gradients for different tasks will be different for different GVF predictions. And this magnitude will scale linearly with the frequency and the size of the individual cumulant. So it will be quite different across predictions. And this means that the updates from the different predictions will basically be reweighted accordingly in terms of how much they contribute to shaping the shared parameters. So if we actually want these trade-offs to be sensible, we need to think about them, because otherwise we'll just be making some trade-off, but these might not be the trade-offs that we actually want for our agents. To understand how important and also how difficult the task is, and how much the magnitude of the gradient can actually differ when making different types of predictions, I think it's good to consider the graph in this slide. So these three plots were generated by showing the gradient norms during training of a value-based agent on different Atari games for 3 different types of agents. So the different Atari games here constitute different tasks that you might make value predictions for. And in all the 3 plots, the lines correspond to different percentiles of the magnitude of the gradient norm. So this means that the width of these distribution gives you an idea of how diverse gradient magnitudes can be across different tasks of different predictions. In this case, the values, predicting the values in different Atari games. And what you see is that on the left, and this is vanilla Q-learning, the magnitude of the gradients actually spans 8 orders of magnitude, depending on which task you're in, with basically gradient norms ranging from 10 to the -2 to gradient norms in the order of the millions. And in the second plot, we show what happens if the individual rewards are clipped to a small -1 to +1 range, and then again, vanilla Q-learning is applied. So this reduces the range, but it's important to see that the gradient norms actually still span almost 4 orders of magnitude. And this is because it's not just the size of the individual cumulants that you're predicting in a different task that counts. Even if the individual rewards are of a similar size, the frequency of these rewards will be different between tasks. And the gradient magnitude actually scales with the value magnitude, not the magnitude of an individual reward. And furthermore, if we look at even at the individual tasks, the gradient magnitude actually changes during the course of training, because as the agent's behavior changes and the number and the size of rewards that the agent collects changes, so does the magnitude of the updates. And this is already a problem if you're training deep RL agents on individual tasks, because you can imagine how hard, for instance, it can be to tune hyperparameters, so the learning dynamics can be so different across tasks. But it also means that any naive multitask prediction problem, such as predicting auxiliary GVFs, will be really hard to get right unless you do something to control how you're trading off the demands from different tasks. Because ideally what we would want is that across the different tasks that we're making, gradients look like in the third plot on this slide, the green plot. Here you can see that across all of these prediction tasks, the gradient magnitudes are actually confined within a reasonably small range. And this means that we can then be explicit. Since we can assume that the gradients themselves have a similar magnitude, then we can choose explicitly how we trade off between the different tasks. We could just assign an equal weight, in which case, given that the gradients have an equal magnitude, then they would equally shape the representation. Or we can choose, for instance, to put a bigger weight on some task, which we consider our main task, and treat the others as auxiliary tasks that maybe contributes to shaping the representation, but with a smaller weight. The problem is, how do we get there? How do we get to the point where our gradient updates have a comparable magnitude across all the many different predictions and all the many different tasks that our agent could be trained to learn? So the way we get there is by using what is called an algorithm, using an algorithm that is called pop art, which so that those plots are actually generated by running a vanilla Q-learning algorithm, but with pop art on top. So, but before I delve into exactly how this algorithm works, it's good to discuss another thing, which is if the issues can be so dramatic when training deep RL systems to make different predictions, why isn't it usually discussed in supervised learning? Because also in supervised learning, we sometimes use a multitask system. And the reason is that in supervised learning, we typically assume fixed data sets. And this means that we can easily normalize both inputs and targets across the entire data set for any number of target variables that we want to predict. And everything will always be well behaved. And this is actually what we do in supervised learning. We just don't even think much about it, where we normalize variables before feeding it into a deep learning system, because it's such a trivial pre-processing that it doesn't require much thought. But the problem is that in reinforcement learning, we do not have access to a full dataset. And the scale of prediction is even non-stationary, so it even changes over time. Which means that any normalization scheme will need to be adaptive to always normalize appropriately across the duration of training. And this is a much more complicated system, and that requires to actually think deeply about what we're doing. Luckily, this problem was already addressed. So for instance, there are a few different ideas that we propose in the literature, but one that I want to discuss today is the pop art algorithm from the plots in a few slides ago. So this was introduced by Hado and me a few years ago. And the algorithm works in 2 steps. So the first step is what is called adaptive target normalization. So consider any one prediction that you're making. So for instance, one of the GVFs. On each update, you will typically observe some target for that prediction. Could be, for instance, a Q-learning target, which you can construct for whatever cumulant you're learning a GVF for. Then what you can do with pop art is to normalize this target adaptively by keeping track of the first moment mu and the second moment nu of the targets for that prediction. So for instance, by doing some exponential moving average of the targets associated to one of the GVFs. And then you can update the network outputs to match not the original target, but on each step use a normalized target that is constructed from the target, for instance, the Q-learning target, by subtracting the first moment and dividing by the variance sigma, which is estimated from the first and second moment by just subtracting the square of mu from nu. And this will basically provide you a gradient update that is much better behaved in terms of magnitudes, irrespectively of what was the size of the rewards, what is the frequency of the rewards, and so on. And this means that if you apply this normalization independently to each GVF, the gradients that you will apply to the shared parameters of the network will contribute equally to the shared representation, instead of having one or more of the auxiliary predictions dominate the entire learning process. Importantly, when doing this kind of normalization, you can still recover the unnormalized Q-values by just multiplying the network outputs, which are trained in this normalized space, by these statistics sigma and mu. And this is important because you actually need the unnormalized values in certain circumstances, for instance, to construct targets via bootstrapping. The problem with the adaptive normalization, as we discussed it here, is that every time you update the normalization statistics, which we typically do on each step because we're just keeping a moving average, you're actually normalizing the update in the current state, but you're inadvertently changing the unnormalized agent predictions in all other states. And this doesn't seem good, because there is no reason for indiscriminately changing the value of all other totally unrelated states. And also, it not only seems a bit fishy, but it also concretely adds, for instance, non-stationarity, which we know can make life harder for our prediction algorithms. But luckily, we can actually prevent this from happening at all with a very simple trick, which I'll discuss in this slide. And this is based on the observation that most neural networks typically have a final fully connected or otherwise linear layer at the very end. So that you can effectively write the network outputs as a linear transform of the activations of the last hidden layer. So the unnormalized Q-values will typically be some matrix W times phi plus a bias vector B for a suitable W and V, and a suitable hidden representation phi, which in general will include any number of nonlinear layers, for instance, some convolution layers with some reload activations and so on. The insight from pop art is that every time you change the normalization statistics, you can actually undo this change in terms of the unnormalized predictions by making a reverse update to the weights and biases of the last layer. And this can actually be done with a very simple formula in an exact way. The way pop art does it is by multiplying the weight matrix by the ratio between the old and the new scale factor, and updating the bias as well with this slightly more complicated expression which is showed on this slide. If you do this, then we get the best of both worlds, because on each step we can still normalize the targets in our gradient updates as in the previous slides, but the unnormalized predictions that we use, for instance, for bootstrapping are not affected by this continuous change of this normalization statistics, and this prevents any instabilities. This approach has been actually very successful in the past. So for instance, in this plot, you can see what happens if you train a single agent to make value and policy predictions for 57 different Atari games, with all these predictions sharing the bottom layer of the network. The version with pop art is the one showed in orange, and you can see how it performs really much better than any naive baseline that does not normalize the updates for the different tasks. So the orange line actually gets to above human performance in aggregate across the 57 games, while the other baselines actually struggle to reach even 60% of human performance. But while this plot shows it specifically for the case of Atari, it's important to notice that the approach is in no way specific to Atari or this specific multitask setting, and can be used whenever you want multiple predictions to use a shared representation, but you want to trade off in a sensible way their relative contributions, as for instance in a GVF-based auxiliary task scenario that we discussed in the previous slides. In this section, I want to discuss a few more advanced topics in GVF learning that we don't quite know yet how to tackle and are therefore still a very active area of research. And I won't go into too much detail of the specific solutions, as the specific methods used to address these issues will likely change as our understanding of these problems improves. And instead, I will give you a brief overview of what these problems are and just a sneak peek of what the frontier of research looks like in this area. The first important topic that we need to make progress on to really scale these ideas up is off-policy learning. So in the setting we discussed so far, we already have multiple auxiliary GVFs that are only used as auxiliary predictions and are learned from prediction experience that is generated by a different main task policy. Since the GVFs might refer to a different target policy and a different equivalent and a different discount, learning these auxiliary tasks already will require off-policy learning. And as you know from previous lecture, we have some tools to deal with off-policy learning. But the reason I consider this still an open problem is that the degree of off-policiness that you might face in this setting, where you're striving to learn like this rich knowledge about the world and many, many different predictions from a single stream of experience, the degree of off-policiness that you face here might be quite extreme. And so I really think we will need fundamental improvements to our off-policy methods to really succeed in learning this truly diverse predictions about the world as auxiliary tasks. And another reason off-policy learning is interesting is that in the context of GVF learning, it's not only a challenge, an obstacle to overcome, but it's actually also potentially an opportunity, because if we are predicting values for many different cumulants, policy, and discounts, we could, for instance, use the additional predictions not just as auxiliary tasks, but to generate experience that is more diverse and provide an excellent form of exploration, even for learning some main task policy. But how to best do so is still an open problem, and again will require improvements also in how well our methods can cope with wildly off-policy data. Still, even though it is still an open problem, we have at least some proof of concepts that these ideas can work and can provide meaningful improvements. For instance, in a unicorn paper from a couple of years ago, we showed how a multitask system learning about many tasks of varying difficulty, but sharing experience between all these tasks so that each prediction was learned off policies from data generated from behavior that was induced by all other predictions, then this sharing could allow to solve certain hard problems that were impossible if you were only striving to optimize for the hardest tasks. Another important problem that might need to be revisited in the context of GVF learning is generalization. So far, we have treated GVFs as discrete sets of predictions that potentially share a hidden representation but are otherwise learned independently. But how do we scale this to thousands or millions of predictions? Learning about all of them independently might not actually be that effective. So just like learning about the value of each state in the NDP was not very effective. So several people are quite excited about investigating whether we can use a similar approach used to learn values in large state spaces and try to generalize what we learn about one GVC to other related GVC in some large space of predictions and problems. And one concrete approach to doing this is to feed some representation of a cumulant or a discount that we wish to make a prediction for as additional inputs to a single network that makes predictions for all GVFs we're interested in. So instead of having a network that only takes one state and outputs multiple independent predictions, this would be a network that takes the representation of which predictions you are required to make as input, and then basically exposes to generalization both states and goals and tasks and cumulants and discounts by using the same function approximation techniques that we have used to generalize across states. So this kind of GVFs, where we attempt to generalize across different predictions, are referred as the universal value functions that are actually a very exciting area of research in deep reinforcement learning. The third important open problem that I want to mention is discovery. So this is the problem of where do GVFs come from? Even if we know how to learn about all of these off policy, even if we know how to generalize across many different predictions, where do the predictions themselves come from? How do we pick which GVFs to learn about? So in the previous section, we discussed that there are many different ways we can construct GVFs, right? We can construct pistol-based cumulants. We can build feature-based cumulants. We can predict the main task reward under previous policies of the agent. But while many of these work in practice, and while specifically at least the value improvement path interpretation actually gives us at least a relatively principled way of picking GVFs, the research in how to choose what to learn about is really, really far from concluded. So among recent approaches that are quite different from what we discussed so far, I want to briefly mention at least one that we introduced with a few colleagues, including Hado, in the paper Discovery of Useful Questions as Auxiliary Tasks. And here we proposed that maybe we should learn from experience what are the useful GVFs that our agents should learn about. And specifically, we propose to do so by parameterizing the cumulants and the discounts that we want to learn about as neural networks. and then use a form of meta-learning called metagradients to kind of discover online what questions our agents should ask about the world, and then try to learn online while it's learning about the main task, for instance. And this actually resulted in quite a nice performance gains in Atari, for instance. The final topic for today is what is referred to as distributional reinforcement learning. In all our discussions so far, if you think about it, GVFs were still representing predictive knowledge, but in the form of expectations. So expectations of the cumulative discounted sum of some scalar quantity, as usual. Another approach, though, that has been proposed is to instead move towards learning distributions of returns instead of expected value. So this generalizes the usual prediction problem in a different direction. So instead of changing the cumulant or the discount or the target policy that we're making predictions about, it changes the type of predictions that we make, so that we predict not expected values, but full distributions of return. So while we generalize in a different direction, though, it's good to realize that similarly to how predicting many GVFs can help with representation learning by providing some auxiliary task effect, learning distributions instead of expected values could also provide a richer signal that could result in better and more robust learning. However, there is an important distinction between these two approaches. When we, for instance, are learning GVFs, as in the methods as in the previous slides, we can reuse the same algorithms from the previous lectures since the beginning of the course, just apply them to different cumulants. The problem of learning return distributions actually requires to extend our temporal difference algorithms in quite interesting ways. And there's several concrete approaches that have been introduced in recent years, but I'll discuss just a couple to give you at least a feel of how you can change temporal difference algorithms to deal with distributions instead of expectations. So the first instance that I want to talk about is what is called the categorical DQN agent. And the objective of this agent is to learn a categorical approximation of the true return distribution. So how do we do this? Well, first, the agent needs to define some fixed combo distribution to act as a support for expressing the categorical approximation of the returns. So for instance, we might allow the return to assume any fixed value between -10, -9.9, -9.8, 9.7, all the way up to +10. And then what we might do is we use a neural network to output now not the expected value, as we would do traditionally, but a vector of probabilities associated to each element of this support. So that you can still recover the expected value by, for instance, computing the dot products between the fixed supports, this calm distribution that we have defined, and the network probabilities through predictions. It's important that you can still recover the expected value because it means that this is a strict generalization. So we could, for instance, still do what we do traditionally for selecting actions. So we could, for instance, still select actions according to a greedy policy with respect by choosing the action with the highest expected value. But importantly, the way we learn these values has now changed because instead of learning an expected value, we have to learn a suitable probability predictions over a fixed categorical support. So how do we do this? How do we update probabilities that the probabilities that we associate to each possible value of the return? Well, it turns out that our temporal difference algorithms can actually be extended to this distributional setting in a relatively clean way. So let's look into how this works. So as usual, we consider a transition. So a tuple consisting of a state st, a reward rt plus 1, a discount gamma, and a next state st plus 1. What we can do then is to take the network predictions in st plus 1. This will provide, in some sense, our bootstrapping. And but take the support of these predictions and shrink it by the discount gamma and shift it by the reward rt plus 1. Then this transform the distributions will be a reasonable target for our predicted probabilities in the previous state, st. This is a really vanilla transposition of how bootstrapping works for expected value, but with an important caveat. And the caveat is that when we shrink and shift to the support of the distribution that we are bootstrapping from, well, the support doesn't match anymore the support of the distribution that we want to update, the one in the previous state, st. So how do we update the probabilities to match these two distributions? Well, what we need is an additional step, which is to project the new support onto the support that we are making predictions for. Reallocating basically a probability as to minimize this projection error. And then at that point, we can just take the KL between the two distributions, so the predicted distribution in ST and the shrinked and the shifted distribution in the next state, and just minimize this KL to update the probabilities in ST. So this actually was shown to work really well in practice, and as a result, it's kind of sparked a whole lot of new research in this area, because focusing either on how to use these distributions, so can we do more than just provide a richer learning signal, and also a lot of research on how we could alternatively represent and learn distributions of return. So ideally to go beyond the somewhat crude categorical approximation that I just described. So for instance, just recently, quantile regression was proposed as a way to kind of transpose the parameterization from categorical DQN, so that instead of adjusting the probabilities of fixed supports, we instead adjust the support associated to a fixed set of probabilities. So this provides often better result because the support can now move around to approximate the distribution as well as possible, and is not constrained to a fixed range that is arbitrarily defined at the beginning. And this means that it is strictly more flexible, because the categorical approximation could instead be quite sensitive to the choice of the bounds of the fixed support. And then of course, there are more extensions that you could think of. You could maybe adjust both probabilities and the support. And there is a lot of ongoing research on this problem that I think is quite exciting and interesting.